Um, okay, it's 10:03, so let's get started. Good morning, everyone. Welcome to CCMMP seminar series. I'd like to begin by acknowledging the Wurundjeri people of the Kulin Nations as the traditional owners of the land on which our Parkville campus stands. I also acknowledge the traditional custodians of the various lands on which you are all joining me from today. I pay my respect to their elders, past, present, and emerging, and to the Aboriginal elders of other communities. My name is Dongju Lee. I'm a PhD student at Monash of CCMMP. For the seminar, we have a housekeeping rules. The seminar will be recording, and the recording will be available on our website after the seminar. The talk will last for 40 to 45 minutes, followed by a Q&A sessions. So please feel free to ask questions during the Q&A session by typing or raising your hand. Also, during the talk, please keep your microphone on mute. Today's speaker is Dr. Max Clabbers. He is a postdoctoral scholar in the lab of Tamir Gonen at the Department of Biological Chemistry at UCLA. He obtained his PhD in structural biology at the Biozentrum, University of Basel, in the group of Jean-Peter Abrams. And then he worked as a postdoc in the lab of Xiaodong Zhou at Stockholm University for 2 years. Currently, his research is primarily involved with developing novel methods in electron crystallography for structure determination of inorganic or organic compounds, natural products, and macromolecules from small crystals. His research focuses on developing methods that integrate cryo-EM focused ion beam milling and microcrystal electron diffraction to determine atomic resolution structures of membrane proteins and identify the ligands that bind and regulate them. Now I hand it over to Dr. Clabbers.
All right, great. Thank you for the introduction, and also thank you for the invitation to talk to you here today. So for my seminar today, I would like to highlight some of our recent efforts that we made in protein structure determination of membrane proteins using alkaline diffraction. And I would also like to show some of our recent results where we demonstrated we could have a substantial improvement in both our data quality and resolution by using data collection using Elton counting on direct Elton detectors. And this then enabled us to solve 2 protein structures ab initio, and also to identify individual hydrogen atoms in our protein data. But first, I'd like to start off with just a short introduction. And in this diagram that I've sketched over here, I am showing what is sort of a typical workflow that's involved in macromolecular structure determination using alkaline diffraction. So we start out all the way on the left, where we have our crystallization. We grow our crystals in solution. We then take about 3 microliters of this crystal slurry and deposit it onto a standard alkaline microscopy grid, similar as to what you would do for single particle. All the excess liquid is then blotted away, and then the grid is rapidly vitrified in liquid ethane. We then transfer our sample to the alkaline microscope, and here we collect our micro-D data using the continuous rotation method. We can then index the diffraction data, get the reflections, and we can integrate their intensities. And we know that the intensities of our reflections are going to be proportional to the square of the structure factor amplitudes. However, then the problem that we're facing, and this is generally true if speaking about crystallography, is that we don't have any ways of retrieving the phase information directly. So here, for phasing, we have to rely on other means. And typically, this is done in our case using either direct methods or molecular placement. Once we have done the phases, we can then get an initial map. And after final sort of model building and refinement, we end up with a final structural model. Now, if I were to summarize this all in just one sentence, then what we're basically trying to do here is emulating what is a X-ray diffraction experiment that you would do with a synchrotron. However, instead of a synchrotron beamline, we're using a alkaline microscope. And instead of X-rays, we're shooting alkanes at the sample. And the reason why we do want to do this with electrons rather than X-rays, there's three main reasons. First of all, electrons, they have stronger, or relatively speaking, they have stronger contrast for visualizing the hydrogen atoms if we compare it to X-rays. Second, because electrons are charged particles, we actually observe the electrostatic potential of the atoms in the crystal, and this gives us the possibility to actually derive the charge states of atoms. And perhaps most importantly, because electrons are several orders of magnitude less damaging than X-rays, we are able to go to much smaller samples and maybe a micron to a nanometer scale that are beyond the reach what you can study with X-ray crystallography. And this is very relevant as one of the major bottlenecks that's inhibiting structure determination in structural biology is failing to grow crystals that are sufficiently sized and ordered to be studied by X-ray diffraction. So you have all these, for example, microcrystalline fragments, as I'm showing here on this slide as an illustration. These are too small for X-ray diffraction. If you would have this in a crystallization trial, normally you might actually discard those. But using Electron diffraction, we can actually get high quality structures from these small microcrystals. So how does that look in practice? So one example that I typically like to show is this project here, which I did when I was back in Stockholm. This was a collaboration together with Bastian Kobe at UQ and Thomas Fay at Griffith. And they were interested in MyD88, which is a signaling adapter protein. And they would observe that after expression and purification in solution, this MyD88 would sort of naturally assemble in these very thin protofilaments that were about 100 to 300 nanometer thin. Too small for X-ray diffraction, but they were ideal samples for micro-ED. So they sent us the sample, and we pretty much just took 3 microliters of this solution, pipetted it onto a standard polycarbonate grid, and blotted away any excess liquid, transferred to the Electron microscope, and we were then using the SA aperture. We were able to really isolate those single thin filaments, and we were able to get high quality micro-ED data up to about 3 angstrom resolution. And this then enabled us to solve the structure of these MyD88 filaments at 3 angstrom resolution. And the structure that we got was actually remodeled compared to previously known monomeric NMR or X-ray structures. And so this was a very, I think, good example of where sample prep is pretty straightforward, and relatively straightforwardly we could directly apply our methods to these samples. Now, fortunately, it isn't always this easy. And one major complication that we're facing when having to deal with protein crystals is the sample prep, and especially for those samples that are grown in, for example, very viscous media. And that was the case here, where we were interested in these metalloenzymes. They grow these beautiful thin plate-like crystals. They're maybe only 200-300 nanometer thin. However, because they were grown at a relatively high concentration of PEG, and this made the solution very viscous. And therefore, it was very difficult to actually get a thin layer, because with blotting, we couldn't really necessarily remove all the excess material. And this made that we couldn't really collect any high quality data of those crystals. Getting this to work was very involved, and we needed to come up with some rather involved way of using pressure-assisted backside blotting to eventually be able to actually get a thin enough layer of ice so we could get our diffraction data to 3 angstrom resolution. And this then allowed us to actually solve the structure of this novel metalloenzyme. And so this kind of works, but that was more of a ad hoc measure that we had to take. But to routinely deal with these kind of samples, we needed to come up with actually better ways of how to access the sample. And it's not only really the solvent or the crystallization conditions that we grow it in, it's also the crystal size. As there is an optimal size of which we can use for micro-ED. I'll get back to that a little bit later. But in case you have crystals that are more than a micron thick, you might want to think about actually getting thinner fragments. And one way we can do that is using fragmentation. And here you, for example, would use sonication, you would use vortexing. And this way, even if you have a bit larger, like micron-sized crystals, you can get smaller microcrystalline fragments that can then be used for structure determination. So personally, I'm perhaps not too big of a fan of this approach. I usually already find that just by pipetting the sample up and down a few times, you already start to break the crystals. If you have a soluble protein, then yeah, this can work. But if you, for example, have membrane protein crystals, which are more fragile, then this approach will usually actually more likely destroy the crystals. I still think this is a valid way to prepare sample if you, for example, want to actually crush the crystals, make smaller fragments, and use this then later on for seeding. But to routinely deal with these samples, we need to have better ways to deal with crystals. And one way how to do that, and this was actually introduced by several groups in the field at around the same time, is using focused ion beam milling. And here we're using a dual beam pFIB SEM, and we use then a gallium ion beam to systematically remove any excess material. At first, we do this with very coarse, larger step sizes, where we use high current. And the closer and closer we get to our final lamella, the lower the current and the smaller the step size that we take, until we end up with a small, very thin lamella. And this way, we can pretty much use crystals of any size, and crystals that are in very thick layers of ice, thick layers of solvent. That does not matter. We can remove all of the excess material, and we can make these crystals available for structure determination using micro-ED. And importantly, we also demonstrated actually, even from these small crystalline lamella, that we can still get high quality structures. The question at this stage then still was how thin or how thick should we actually make our lamella? What gives us the best data quality? And this is what we then systematically investigated here by milling crystals of proteinase K to thicknesses that corresponded to multiples of the inelastic mean free path. And we found that we could get high quality micro-ED data up to thicknesses of about 2 times the MFP. If we would go to thicker crystals, then we would very rapidly see that the data quality started to deteriorate, just because the thicker the crystal, the higher the chances on inelastic scattering, on absorption. And we do see here that the noise is just much higher, and we almost cannot see any spots anymore above the noise if we go to 3 times MFP. Now, surprisingly, there wasn't much of an improvement by going to much thinner crystals, for example, to like 1/2 times the MFP. And this also has to do with the fact that you're going to have a trade-off, because you also need a certain number of repeats. You need a certain number of unit cells to actually amplify the signal to get this Bragg boost to your data. So having more unit cells will actually give you a stronger signal up to the point that you get diminishing returns when the crystal is getting too thick, and then multiple scattering events and absorption are going to take over. So typically, we do aim for about 1 time the MFP, and I found also that this is very reproducible. Each and every time I can get more or less 300 nanometers reproducibly with this approach. But these results show that if the crystal is a little bit thicker, that's not going to mean that the data is going to be much worse if we do that. Truthfully, it will also really start to depend on the sample that we're using. If you have, for example, something with a very large unit cell, then maybe you want to be rather on the thicker side. If the crystal, for example, is very soft, because sometimes you see that when milling, the crystal is just not as robust, then also you want to be maybe on the thicker end of this limit. But at least here we show that even if the crystals are a little bit thicker, we can still get high quality data. And interestingly enough, we saw the same trends when we repeated this experiment at 120 and at 200 keV, as illustrated here for the resolution, IVA sigma, and CC half as multiples of the mean free path. So now that we basically figured out that we can use this FIB milling to prepare our crystals, then how actually do we apply this then to some sort of useful biologically relevant problems? And one of the areas where traditionally electron crystallography has been involved with is the crystallization of membrane proteins. Now, these are notoriously difficult to express, purify, and crystallization typically needs the use of certain detergent and lipid mixtures to sort of mimic what is a native lipid bilayer. This is very challenging, and very often, even when crystals grow, they only grow to a micron size. So that makes actually these samples potentially interesting for micro-ED. They are small enough, and with the FIB milling techniques that I just introduced, even if the viscous liquid cannot all be removed, we can still access them and use them for structure determination. However, in practice, there was another issue, and that is kind of illustrated here, where I'm showing here 2 grids in the fFIB-SEM from the ion beam view, where we have crystals of the human VDAC, which is a voltage-dependent anion channel. And these crystals were grown in lipid detergent cells. Now, we can get them onto the grid, and with blotting, we can remove some of the excess material. However, the problem that we then face is where actually do we have crystals? Because we have these very thick layers of maybe a few microns in some places of lipids matrix that is covering the crystals. And it is very difficult for us then to actually locate our microcrystals and where should we actually target and where should we mill. Fortunately, screening a few grids, there's also some areas where the lipid matrix was thinner. And here we could find, and it might be difficult to see, but on the left, shown by this blue outline, you can see what's sort of the contour of a very thin plate-like crystal. So the crystal was perhaps maybe only 300 nanometer thin. And you can sort of vaguely, below this lipid matrix, see the contour, these sharp edges of where you have a crystal. So once we found that, then could make, using the gallium beam, we could make thin lamella of 200 nanometer thickness of these crystals. And from just this one single thin lamella, which is shown on the right, it was then possible to solve the structure of the human VDAC at 3.1 angstrom resolution. And this was the data that was 80% complete. Interesting enough, besides that we can see the structural model, we also observed between these channels, we saw all this extra density that is shown here in blue, which was indicating the positions of the lipids, indicating the packing of the lipids and the protein in this structure. So this worked very well for this particular case. However, that didn't really still solve for us how to find our crystals. And this is getting increasingly more complicated if we consider even more viscous sample conditions. As one method that's very often being used to crystallize these membrane proteins is using lipidic cubic phase, for example, for the crystallization of G protein coupled receptors. This is even a lot more viscous. It almost has sort of a toothpaste-like consistency. It's very sticky. And as illustrated on the left, with blotting, we can't really remove anything. If you try to blot away, the drop will just stay on the grid, and there's no way you can actually make it thinner. So one way that people came up with to actually how to deal with these samples is to use what's called a phase conversion, where, for example, we try to dilute the LCP to a less viscous sponge phase. And this sponge phase, then actually you can blot, and this way you can get actually a sort of a thinner layer of lipids, and we can then find and target the crystals as is illustrated on the right. However, this approach isn't really ideal. It has a few drawbacks. For example, not every condition that we can grow onto plates, we can also reproduce by growing in syringes. Growing the crystals in syringes does also require a lot more material, which sometimes you might just not have. And perhaps the most important reason, the phase conversion might actually affect the crystal, might affect the crystallinity, as there is a reason why we need this LCP to facilitate the crystallization. So instead of doing this phase conversion, we came up with a different approach where we express purified these GPCR crystals of the human adenosine receptor. And on column, we then labeled these using either Cy3 or dye 550. And these fluorescently labeled crystals were then set up on plates. And for the sample prep, we then just looped one entire drop onto a LIT microscopy grid. And this was then transferred to a plasma fFIB-SEM with an integrated fluorescence module. And so what we see here on the left, we have these huge piles of LCP. They are up to maybe 100 micron thick. It's really very vast material. You can't see through it. And there's no way of actually locating where we can find our crystals. So what we then did is we moved to the fluorescent mode. And what we can do is we can take a let's go back. We can take a sort of a Z stack in Z in depth, so that we can get the fluorescence signal all the way from sort of the top of this LCP pile all the way to the bottom where we have the grid square. And this way, we were then able to identify our microcrystals that are indicated on the right here in the middle, where we have both the position in X and Y, and also we have the depth in Z. So this shows us pretty much exactly where we need to mill and where we can target then our crystals. We can then go back to our view in the fFIB SEM, and we can overlay this fluorescence stack with the SEM stack. And this way, we exactly know then where we need to start milling and where we can target our crystal. We then use the plasma fib with either an argon or the xenon beam to systematically remove these layers of LCP until we approach the crystal, which is shown on the right, where we can still see the fluorescence signal in this 250 nanometer tin lamella. And while doing this, we keep sort of going back and forth between the SEM mode and between the fluorescence mode, so that we always make sure that we're not overshooting and we're not actually milling into the crystal. And using this approach, we were then able to get the structure just from these thin single microcrystals up to 2 angstrom resolution of the human adenosine receptor. And interesting enough, we were also able to then resolve the bound antagonist, the ZMA, and we also saw density surrounding these transmembrane parts, indicating the positions of the cholesterol molecules that were surrounding the receptor. And altogether, I think this really gave us a very, at least now, robust way of setting up crystallization trials, finding our crystals, and then producing lamella to get structures from these difficult to target proteins. We also recently got access to a Leica tender, and on this machine we can actually very quickly get a full grid atlas in fluorescence mode that we can then correlate to the fFIB SEM. And this way we can rather quickly screen a few grids, select the ones that have interesting crystals, and then we go to milling to then get a structure model. Right. So this far, I've mainly been talking about sample prep, which is one major area that we have been working on. Another area that we have been interested in a lot is optimizing data collection. So for data collection, we're using what is called the continuous rotation method, which is analogous to how you would collect data in crystallography, where we are continuously rotating a single crystal about the rotation axis. And this allows for very complete sampling of reciprocal space. Now, because the crystals that we're working with are relatively small, one major sort of complication that we need to take into account when considering sort of our optimal data collection strategy is radiation damage. And this is always what we have to take care of if we work with these crystalline biological specimens in cryo-EM, as we can already start to see the effects of radiation damage on like a global scale. For example, during prolonged exposure, we start to lose our high resolution information. The noise starts to increase. We start to lose the intensities that become lower and lower if the exposure gets longer, because we're just losing those the crystallinity, those longer order contacts. We also start to see the effects of radiation damage at a more structural scale, where at a exposure of about 1 electron per square angstrom, we already start to see breakage of the disulfides. And at exposures of 3 electrons per square angstrom or higher, we do start to see decarboxylation of the acidic side chains. So therefore, when working with these crystals, we have to go to cryo conditions, not just to preserve our sample in its native hydrated state from radiation damage, but also to preserve it against the vacuum of the electron microscope. And this also does mean that when setting up our experiment, we are limited in the kind of the exposure and the exposure time that we can use. And this dictates that we always have to go to very low exposure conditions to outrun the radiation damage. And the sample is a very important factor of how we can set up our data collection. The other important factor that comes into play is the camera. And here in micro-D or in diffraction in general, we can really benefit from having fast, so high frame rate, low dead time, fast readouts, and highly sensitive detectors that can keep up with the speed of data collections, even under very low exposure conditions. And one of the reasons that micro-D was only really feasible last maybe 10 years was the introduction of the much faster scintillator-based CMOS detectors, hybrid pixel detectors, and also direct electron detectors that allowed for continuous data collection in movie mode. Yes. So for data collection, we here were really interested in testing out the direct electron detectors. So these are very commonly used in cryo-EM, especially though more in the imaging application. So if you have, for example, single particle analysis, electron tomography, then all these labs will use direct electron detectors. However, to date, no one has really used these for diffraction experiments. And the main reason for this is kind of that in diffraction, our signal is going to be focused in the bragg spots. And this means that they can become very intense, especially at low resolution. And these very intense spikes, they first of all, they actually potentially could damage the camera. And secondly, we want to make sure that these very intense spots stay within the linear range of the camera. Now, the frame rate and the linear range of these direct detectors is going to be less than, for example, what you get with a hybrid pixel detector like a Pilatus or an Eiger or a Medipix. And so when setting up our experiment, we really needed to make sure that we lower the exposure enough so that we stay well within the linear response per pixel of the camera, and that we minimize any coincidence loss or double counting. At the same time, meaning if we're using lower exposure, it also means that in turn, the signal that we can expect to get out is going to be weaker. And this does complicate how to set up our experiment. And this made that actually we had to rethink the way how we were collecting data. So in order to make use of these direct electron detectors, such as the K3 or the Falcon 4, we needed to come up with a new approach where we are significantly lowering our exposure by using the smallest C2 aperture. We go to a very large spot size. We spread the beam to a very large area. We can then reduce the number of counts that we get by introducing the SA aperture. And in part, we can then compensate for sort of the weaker signal that we expect to get by actually starting to rotate slower. And this way, the bragg or the reflections will be in bragg condition for a little bit longer, thereby increasing the signal. And we can also optimize the signal to noise ratio by using focused ion beam milling, as I showed before, and milling the crystals to an optimal thickness of about 300 nanometer for micro-D data collection. Now, the main reason why we were really interested in testing these direct electron detectors is that by getting better data, by getting more accurate intensities, we can expect to get better structural models, and we can expect to see a much higher level of detail in the structures that we can get. And this is what we have been demonstrating over the past few years, that by improving our data collection, by improving the hardware, we get better structures, better R factors, better models. And it's not just about that. It's also important if we, for example, consider phasing. As to date, all the protein structures that have been determined by micro-D have been done so using molecular placement, and thereby relying on having either a homology search model or a model from structure prediction, such as AlphaFold. Now, this isn't necessarily a bad thing, as even with molecular placement, we are able to solve novel structures. However, the solution that we get is inherently going to be biased by what we put in, and a lot of our molecular replacement solution is just going to depend on the prior structural information that we put in. So we were interested in also exploring different phasing strategies, not just to reduce this model bias, but also because these different alternative ways to phase the structure would be relying just on the accuracy of our intensities with no additional structural information needed. So it really will be a measure for our data quality. So this is what we set out to do here, where we demonstrate ab initio protein structure determination of two proteins using electron counting data collection on a Falcon 4 direct electron detector. We demonstrate this for triclinicalized design at 0.9 angstrom resolution and for proteinase K at 1.5 angstrom. So in case of lysozyme, we grew the crystals, deposited them onto a standard grid, and we then made thin lamella using the fFIB SEM, and those grids were then cryotransferred to the Krios microscope. When transferring the grids, we always do make sure that we rotate the grids so that the milling direction is always facing perpendicular to the rotation axis on the microscope. That's shown here by the yellow dotted line. We then set up our experiment for low exposure data collection by choosing the largest spot size, inserting the smallest C2 aperture. And one advantage of having a high-end microscope like the Titan Krios is that we have this third condenser lens. And because of this third condenser lens, we have a very wide range in which our beam is going to be parallel. So we can easily sort of adjust the exposure by either expanding or condensing the beam. So here we spread the beam to a diameter of about 25 micron. We can then, as is shown in the middle, select the diffraction signal of only a much smaller area using the SA aperture. And here we can select the diffraction of only an area of 2 micron diameter, as is shown by the blue circle in the middle, directly on the lamella. So we only have really diffraction from a much smaller area. And what we then do, we manually bring each of these lamella to the correct eccentric height. And then at the same time, we start rotating the crystal. And at the same time, we start to collect our data, as is shown on the right. We do this continuously in movie mode on a Falcon 4 that was operated in counting mode. Each crystal was rotated for about 80 degrees at a speed of 0.2 degrees per second, meaning that just collecting one entire data set took 7 minutes at 2 frames per second readout. The total exposure that we used for each crystal was only 0.6 electrons per square angstrom. And we can see here that these crystals of lysozyme diffracted very well. We can see spots almost all the way to the edge of the detector, which is at a 0.9 angstrom. Now, because in a sense, the rotation method that we're using is so similar to X-ray diffraction, we do have the advantage that for the data processing and also structure determination, we can rely upon existing crystallographic routines that were originally developed for X-ray diffraction, but we can adapt them for our electron diffraction data. So in case of lysozyme, these were integrated and indexed using XDS. We found the triclinic space group, and because the completeness of just one single crystal was relatively low, we ended up having to merge data of 16 lamella to get then a completeness of about 90% overall, up to 0.87 angstrom resolution. Then to face these data, we used what's called sort of an ab initio fragment-based approach, where the only assumption that we're pretty much making about our structure is that it's gonna consist of secondary structural elements, such as beta sheets, such as alpha helices. And we can use these standardized fragments with ideal geometry for an initial molecular placement search. And we found that in case of lysozyme, we were able to get a solution from a fragment that was only 3 polyalanine residues long, or 15 atoms, which is just a very small percentage if we consider that the entire asymmetric unit does contain 1,001 non-hydrogen atoms. However, at this stage, after initially placing this fragment, it was still difficult for us to judge whether we've actually found a correct solution. If we look all the way on the right, then the map that's calculated just from this initial sort of starting phases still looks very noisy. It's difficult to make any interpretation from model building or even to judge whether this solution is correct. So what we then had to do in the next step is follow this up by density modification. And density modification made a big improvement if we compare the situation on the left to the right. Then on the right, we can see that after density modification, we can now clearly see sort of the envelope of the protein. We see where we have the solvent channels in between the proteins. And if we zoom in on the smaller insets, we can now actually start to see that we have individual atoms that are resolved, whereas on the left, it's just all noisy. So this density modified map, together with the starting fragment and the sequence, was then used for automated model building in Buccaneer and RevMech. And Buccaneer was able to then rebuild the entire structure model, so successfully modeling the backbone, and then placing all the side chains based on the density. And we end up with a high quality epination model at 0.87 angstrom resolution. Our work and our free of 18 and 23%. And this was all done at a total exposure of only 0.6 electrons per square angstrom. And you can also really see this here on the next slide, where I'm showing each of the individual side chains. And we can see here that even in the density modified map that's shown in orange, we can clearly distinguish individually resolved atoms at atomic resolution. And we can also clearly already identify from the density modified map the different side chains in the map. So this was the first time that we really were able to collect atomic resolution data of a protein using alkaline diffraction methods. And interesting enough, in these data, we also started to see some additional peaks in these maps. And these are indicating the positions of the hydrogen atoms. So we were interested whether with these data, we could actually successfully resolve those hydrogen atoms. So what we did was we took this map and the model from Alta building. We re-refined it, added some side chains and alternate conformations, and we then calculated what is a hydrogen omit map. And this is presented here, where I'm showing the hydrogen omit map with the green and red for positive and negative density. And we did a peak search, and the peaks are shown here as the small green spheres. And we counted each of these peaks as a potential hydrogen atom if there were at least 0.5 angstrom within a from a known riding position, and if there were at least 2 sigma or higher above the noise. And in this fashion, we were able to resolve over a third of the hydrogen atoms in the structure. Overall, the hydrogens on the backbone are a little bit more stable. There's a little bit less flexibility, and we do see a relatively higher percentage of the hydrogens there. And we can also see these hydrogen atoms that are involved in hydrogen bonding interactions that are stabilizing secondary structure. For example, on the left, we have these 2 very short anti-parallel running beta sheets, and we can see these 3 hydrogen bond interactions that are stabilizing this structure at peaks that are 3 sigma or higher. So lysine is a relatively small structure. It has about 3 to 5 helices. And in the largest alpha helix that is shown here, it's 12 residues long. We were able to identify 6 out of 10 possible hydrogen bonding interactions at peaks of 2 sigma and higher. So these were very promising results. We then also looked at the hydrogen atoms in the side chains. So overall, in the side chains, we have a much higher sort of flexibility. And this makes it a bit more difficult to actually identify the hydrogen atoms. But we were still able to see a substantial number of them. And for example, we can distinguish the protonation state of atoms, as is illustrated for the histidine on the top left. We can see hydrogen bonding interactions, as illustrated here for the aspartate and tyrosine, where we can see a strong peak for hydrogen bond interactions between these 2 side chains. And we can also observe hydrogen bond interactions between side chains and water molecules in the active site. And this is the first time we were able to demonstrate such a complete overview of all these hydrogen bonding networks in a protein structure using alkaline diffraction. Now, the fact that we were able to do all this at atomic resolution using triclinic lysozyme is perhaps not too surprising. So we were also wondering, is such an approach also tractable for a more sort of standard case? So what we did is we repeated the exact same experiment, but this time with crystals of proteinase K. So proteinase K is about 3 times the size of lysozyme, and it has about equal parts alpha helix, beta sheets, and loop regions. The only difference that we really made here is that we did 2 passes. So first, we collected a high-resolution pass that was aimed at getting the high-resolution information up to about 1.5 angstrom resolution. And as you can see at the lower end, close to the beam stop, the intensities are kind of kept at about 20 angstrom resolution. And you can already see that even the low resolution spots, because of all this inelastic scattering that we get from the center peak, they are being shaded, and the uncertainties are higher there. So in order to capture also the low resolution reflections, we did a second pass where we increased the camera length by a lot, so that now we can measure also the low res spots, as is shown on the right, that go from 5.5 angstrom to about 100 angstrom resolution. We did this for 4 lamella. In the end, we ended up using 2 lamella only to get then a completeness of roughly 100% up to 1.5 angstrom resolution. So for these data, we wanted to use the same ab initio approach for phasing. However, the problem is going to be a lot more challenging, as we're having a lot more unknowns. It's a lot larger structure, and also we have a lot less data to work with. So in this case, we were able to find a solution using 4 14 residue polyallyl helices that were then initially placed. And as we can see on the left, the initial map that we calculated from just these starting fragments is still rather noisy. There's not much we can see sort of outside of those helices. So we then, in the next step, used iterative rounds of both chain tracing and density modification in ShellXE. And ShellXE was then able to trace almost the entire backbone. And this trace, together with the density modified map, was then successfully used for automated model building in Buccaneer and RefMech, which was then able to rebuild the entire structure model. So in summary, I'm showing this here again, we demonstrated we could get ab initio structure divination for 2 protein structures, triclinic lysozyme at 0.9 angstrom resolution and proteinase K at 1.5 angstrom, by using alkaline counting data collection on a type detector. And this was largely feasible really because the improvement in the accuracy, the resolution, and also the quality of our data that we got, as any previous attempts at us of trying this using scintillator-based CMOS detectors were not successful. So the data I've shown here were from the Falcon 4. We later also got access to a Catan K3, and here we demonstrated we were also able to get high resolution data from the K3 detector from the same proteins. Interestingly enough, here we actually did not use a beam stop. It was actually because the camera was placed all the way at the bottom of the column. So that made that actually the projection of the beam stop was going to be shading a large part of the detector. So the solution was actually to use it without the beam stop, and we were able to collect high quality data just with that. Then, I don't know how I'm doing on time, but maybe for the last few slides that I have, I also briefly wanted to highlight the use of alkaline diffraction for more organic chemistry and material science, as there's a very high potential for a user case here, as for these samples, structure determination typically is going to be a lot more straightforward. We can go from having a small powder of, for example, a pharmaceutical, deposit that onto a grid. We can look at the level of just one single crystal. We can collect atomic resolution data and get high quality structure using direct methods. We can see the hydrogen atom positions. And this is all relatively straightforward with a much faster turnover that's almost rivaling the speed which you could use X-ray crystallography. What we can do furthermore even is not just look at one sample. We can, for example, screen the grid and look at the entire composition. In case, for example, we have a mixture of different crystals on the same grid, we can distinguish the different compounds and get some information of the composition that we have. And this process is also highly suitable for automation, where we can, for example, use automated data collection to automatically raster, screen through the grid, collect rotation data, process the data automatically. And this can then, for example, be used to distinguish compositions, or, for example, to enable phase identification from synthesis or large mixtures. And then finally, this combined with the fact that with alkaline diffraction, we can get information about the hydrogen positions, we can get information about the elastic potential of the crystal. We are able to actually get a full overview, a full picture of all the interactions, all the potential interactions that are involved in our crystals, are involved in bacterial formation. And I think moving forward, this is also a very interesting and a very useful application of these micro techniques. Right, with this, I'm at the end of my slides. I would like to thank the Goen Lab at UCLA, and for the work that I presented here today, I would in particular like to thank Mike, Johan, and Tamir, and thank you for your attention.
Thank you. It's Really great talk. It's a really interesting topic. Any
Yeah.
questions? Peter, can you unmute?
Yeah, sorry, took me a little while to get to the unmute button. Awesome talk, Max. Really cool. A couple of questions. One, with the low symmetry crystals where you need to collect off multiple crystals, I'm guessing that's a little bit dependent on the crystal shape, right? And how it falls on the grid. Is there any tricks to overcoming flatter crystals, for example?
Yeah, so it mostly has to do, with the symmetry and then also with the shape. Typically, with those plate-like crystals, it's going to be difficult, and they will usually fall, more or less on one orientation onto the grid. People have tried different approaches to deal with that. What we recently saw actually is that when we have, for example, these crystals in LCP or very thick media, and we don't really have a lot of tin, then we are able to find sort of in this big piles of LCP, we are able to find even plate-like crystals at different orientations or even at side views. In case it's just onto the grid, then so one approach is also with milling. We are able to actually get sort of higher tilt angles, because typically you sort of mill at a grazing incidence, but you can also change the milling angle by quite a bit. So even if they're flat, you can still try to get the higher orientations. But in all, it still is going to be annoying to have to work with low symmetry space groups, because it requires a lot of extra work to actually get those higher tilt angles.
Yeah. Another question, if it's okay, if I can ask. What about
Sure.
so you've got I mean the molecular replacement solutions using small helices and etc. It's a little bit like Isabelle Lusson's Arcimboldo net. Are you using that at all?
Yeah, so it pretty much is the exact same procedure that Arcimboldo is using. We in the beginning tried it using Arcimboldo, but that for reasons didn't necessarily really work. At least I didn't really get it to work. So instead, it's really more of a deconstructed approach, because Arcimboldo is using it's using phaser, it's using shellacs. So we kind of deconstructed it, run the steps independently, and that made it for us a bit more also tractable to be able to follow the intermediate steps and to get it then to work. But technically, this exact same approach should work if you would run it from Arcimboldo.
Cool. Thanks very much for a great talk.
Sure. Thanks.
And Richard?
Hi, Max. Really great talk. Thank you. I was just wondering if you could comment a little bit on the benefits of collecting at 300 keV versus 200, and are you consistently collecting on the Krios now, or do you still use 200 keV?
So for now, at least for all the protein work, we are consistently using the Krios. It's mostly also because that 300 keV instrument for us, it has the best setup. We have Falcon 4 detector. We recently also got a Selectress, so an energy filter. So that really gives us very good data. I think still there is some advantage of going to 300 keV. It's just a bit more intense beam. You can have a little bit more thicker sample. The data looks just a little bit nicer if you do it on 300 keV, but there's no reason you could not get any good data using 200 keV. I would maybe go for a little bit thinner crystals, but we can still also, for example, on the Arctica, which is the 200 keV instrument that we use, we can also get high quality data there. But if I have the option, I would rather go for the 300 keV.
And can I ask one quick more question on that? So are you okay with the direct electron detectors? My understanding was we weren't originally allowed to use these for MED.
Yes.
Is that still the case, or are Thermo coming around to it with the Falcon, or what's going on there?
Yeah, so that was especially also for me the case in previous labs. Then when they were doing single particle, then you were not allowed to use diffraction. You were not allowed to direct detectors at all. I think at least we showed here that we can just consistently collect data, and even if we get these highly intense spikes at low resolution, we don't see any apparent like immediate defects onto the camera. So I think that is fine. I still probably wouldn't have the direct beam on there. I would rather still use a beam stop at least. But for just routine data collection, I think it's going to be fine. I think indeed, when we published this, then Thermo wasn't necessarily very happy that people were all asking if they could also, because the camera needs to be disabled to actually use diffraction. So yeah, people were asking Thermo whether on their system they could also actually disable or enable, I should say, the use of diffraction onto the camera. Because if you don't turn that off, then yeah, it will immediately just shut off as soon as you go to diffraction on the Falcon 4. But yeah, I think for us, we've been using it now for the past, I think at least 2 years now, and the Falcon 4 on diffraction, and that has been working fine for us.
Thank you.
And I think, yeah, still, I mean, I think the thing really, I think even we can get away with even higher exposures than what we're using now. They didn't really give a very, I think, strict or a very strict number of what the exact linear range is that we can use. But what we have been using now, we don't really see any strong effects of like coincidence loss. So I think you can use even higher exposures, but of course it's still dark. It's not as good as, for example, perhaps a higher pixel detector, where you just have a much larger dynamic range, much higher frame rate. The downside there is that these higher pixel detectors are usually like much smaller areas, and that makes them still useful for diffraction, but for imaging makes them less useful.
Maria and Lena?
Hi, can you hear me?
Yes.
Thank you. It was a great talk. So I was wondering, maybe it's like a naive question, but in the context of membrane protein crystallography, particularly with eukaryotic expression systems, it can be challenging to obtain sufficient protein quantities. So I was wondering, is there any approach that you follow to determine the right concentration for your protein to be crystallized?
For these setups, not necessarily. I think also most of the work on the A2A was relatively standard proteins. I think the one thing that we did change recently is always just label the protein on column, and this makes it also easier to then, for example, in crystallization trials, actually to figure out if we see fluorescent signal already in the drops, then we can be relatively sure that at least what we see is protein. And then also with the Leica, with the screening, we can already pre-screen grids before we actually use them. And yeah, using that is, I think, one of the major things that we have changed past year in our sort of sample prep workflow, which makes it, I think, yeah, easier to actually not just later on for the milling to identify the crystals, but also during crystallization actually to identify which hits are potentially useful and which ones are just can be discarded.
Yeah. I was also wondering about the concentration of the protein. I mean, I guess it also depends on the protein itself, but I really don't know much about membrane proteins and crystallization. So I was wondering, like, what's the concentration that you usually expect proteins to crystallize, like the membrane proteins? Maybe it's very protein dependent, though.
Yeah, I would say it's I would say anywhere between, I think ballpark like 10 milligrams, 10 mg per milligram.
All right.
Sorry, per milliliter. But it would depend. Yeah, it would depend a lot on the sample. It also depends on like whether you initially get hits or not, and then you might play with the protein concentration to actually grow them smaller or grow them larger.
Cool. Thank you so much.
Yeah. With soluble proteins, I think we've usually actually used a pretty much higher concentrations, because then you have a chance of actually getting smaller crystals. But also that depends. Sometimes it helps to actually lower it.
Thank you.
Any other questions? I've got one question. It's related to the first question. In terms of the shape of the crystal, the height of the crystal is important to get a better data. Like the thinner microcrystals may give better data than the thicker crystals.
Yeah, so there is definitely gonna be sort of an optimal thickness that we can approach. Like ballpark, I would say about 300 nanometers is kind of optimal for data collection. If you go any thinner, the signal is going to become weaker because you just have less crystal volume that's diffracting. If you go way thicker, then actually, you start to have more multiple scattering events, more inelastic scattering, and this starts to deteriorate the signal. This would then also matter, for example, if you use 300 keV or 200 keV. If you have 300 keV, you can get away with a little bit thicker crystal because there's just the MFP is going to be longer for the higher accelerating voltages. But yeah, so it depends. And I think the nice thing really with FIB milling is that we can control this thickness way better as that we were able to do so before. And yeah, you also remove a lot of excess material, which is great.
Okay, we've got one more from Yufeng. Can you unmute?
Hi,
Yeah.
Max. Nice to see you again. Just wondering, it's really great talk. Thank you for sharing all the things thoroughly.
Sure.
I'm thinking for the hydrogen position, what kind of software are you using to determine the position and the bond?
Yeah, so the for the hydrogen map, so that was a routine we did in RefMac. So you can ask so after RefMac in refinement, you can ask it to it's pretty much a hydrogen map where you just let it run a 0 cycle refinement without any hydrogens present, and then you get this difference map from that. But you could also do this, I think, with any refinement program. I think also with Phoenix Refine, with Shellax, you will be able to actually calculate such a map.
Yeah, I find sometimes find some electron densities a bit further. Is that normal for electron or?
Yeah, so this is I didn't really mention this, I guess, during the talk, but what we do, we also made an analysis of the different hydrogen bond lengths that we could find, and what we do see overall is that the hydrogen atom peaks that we find are a little bit further away, so they're more closer to the internuclear distance that you would see in a neutron diffraction, rather than the bond lengths between the sort of the centers of the Electron clouds that you would see with X-ray diffraction. So yeah, overall they are a little bit more elongated. So also there it would be better to actually refine using adjusted bond length parameters for specific either for Electron diffraction, or you can use those for neutron diffraction as well. But yeah, that's something that we did observe, that the peaks are usually a little bit further away than where you model them in sort of X-ray diffraction.
Thank you. That's really cool. Yeah, I'll check more papers, read more. Thank you.
Thank you. It's already 11, so thank you for our today's speaker, Dr. Max Clabbers, again, and thank you for coming our seminar today, and see you next month.